Hello, welcome to online version of Physics 103. In this video, I'm going to talk about work and energy. So first of all, let's talk about work in detail, then we'll talk about energy, all right? So first of all, let's talk about work done by a constant force, okay? So we have been talking about constant acceleration, right? So what in the previous chapters, we talked about constant acceleration. How is acceleration related to force? Force, net force is equals ma, right? So, so we have been talking about constant acceleration. So what is the corresponding force? Corresponding force is constant force. Okay, we don't have to talk about a variable force in this level. So as you know, in high school, work done is given by force times displacement, where F is the force and S is the displacement. So obviously, in our case, we're talking about constant force. Okay, so basically, we'll be talking about the work done by a constant force. So when I say force, your force should be in the direction of the displacement. Let's look at this example here. This guy is pushing the car along this direction to the right, rather. So by how much? By a displacement of S. Okay. So remember, the force and displacement have the same direction. That's why in this case, our work done is simply work equals F times S. Okay. So what is the unit of work? A unit of work is force has the unit of Newton, as you know, and S has the unit of meter. So multiply them together, you get Newton meter. By the way, so Newton meter is also called joule. Okay. In this slide, I'm going to talk about different units of work. So in the previous class, we talked about mainly two kinds of system, right? SI system of unit and English system of unit. This is SI, which is also called MKS unit. And this is British English, also called English system. Okay. So I'm here going to introduce another system of unit, which is called CGS system of unit. So the CGS is related to MKS. So how? So what is MKS? MKS, mass in kilogram, and length in meter, and time in second, right? So MKS. So similarly, CGS refers to, this is C, this is G, and this is S. So what is C? C meaning centimeter. Okay. Here you have meter, here you have centimeter, right? Then kg versus gram. So this is G for gram and S for second. Okay. So this kind of system of unit is called CGS system of unit. So in SI or MKS system, the unit of force is Newton. So unit of distance is meter. That's why unit of work is Newton meter, or you can call it joule. In CGS system, which is newly introduced unit today, so the unit of force is Dian, and unit of distance is centimeter, and unit of work is erg. Okay. And similarly, in the English system, as you know, the unit of force is pound, the unit of distance is foot, and unit of work is foot pound. Okay, FTLB. So in this case, I'm going to talk about the work done by the force, but the force in this case is not is not in the same direction as the displacement. As you can see here, displacement is happening to the right, but the girl is pulling the briefcase in this direction. So this force and this displacement are not in the same direction. So suppose F equals 3 Newton and the displacement S equals 2 meter. then you cannot simply write work as 3 times 2, because this is F, this is displacement, right? Looks like your answer is 3 times 2 equals 6. That's not correct. Okay, this is wrong. So why is this wrong? Because your force has to be in the direction of displacement. So is the force in the direction of displacement? No, the force is in this direction, right? And displacement is in this direction. How come the displacement has occurred without a force? That's surprising, right? So it happens because the force is a vector and can be split into two components. Okay, so that's called resolution of a vector. Okay, meaning you can suppose you have a vector like this, you can split this vector into two parts. So when you split it, you will get two components like this. Okay, so your vector is here. So this is your vector. Once you split this guy, then you will get two components, one in the y-axis, the other one in the x-axis. Okay, there is no longer this guy there because you split it. Now you have just two components, one in the x, the other one is in the y direction. Okay, so now it means you can split your force in two perpendicular direction. Now what is the force you need here? You need the force in the direction of s, meaning you need this component. Okay, suppose this is my initial direction of the force before I split. This is my F. If this is the angle theta, then from this right triangle, right? So this right triangle, so this is, if this is F, this is Fx. Okay, so I have redrawn this triangle here, this triangle over here. Okay, the blue one here, this blue triangle is redrawn here. So if force is let's say 5 Newton, right? Then so, and your theta is something like, let's say 37 degree. Okay, then what is your Fx? Okay, so to find Fx, we use the trig function, right? So cosine function is adjacent over hypotenuse. Okay, so in our case your adjacent is Fx, right? Then what is your let's write here, cosine 37 equals adjacent is Fx, hypotenuse is 5. So from here your Fx is, so from here if you multiply 5 on both sides, then what do you get? These cancel out, then what is your Fx? Fx is 5 cosine 37. Okay, so this Fx is in the direction of displacement. Okay, so from here your Fx is, so from here if you multiply 5 on both sides, then what do you get? These cancel out, then what is your Fx? Fx is 5 cosine 37. Okay, so this Fx is in the direction of displacement. Okay, that's why we have to modify our work like this. Okay, now this Fx is 5 f so my f is 5, cosine theta is cosine 37, then displacement is again let's say 1, right? So if the displacement is 1, then you have your work done like this. So you have to just calculate this, then then 5 cosine 37, you happen to get almost 4 joule. Okay, so this is how you figure out your work done. Now how about the other component of the force? So Other component of force is not useful. Okay, this component of the force is not useful. Only the component which is in the direction of displacement is useful. Okay, now this is the so this is the most general formula for work, right? So in our case, in the previous case, we consider our theta to be 37 degree. But if you consider your theta to be 0, meaning you are applying the force like this, you are dragging the briefcase like this, which is unlikely. But for instance, for now, if you consider your briefcase being pulled or dragged like this way, then the angle between S and F is 0, right? In that case, your cosine 0 is 1, and your formula becomes F S, okay, because this guy is 1, okay, which is similar to the previous formula in the in the previous slide. And similarly, if your angle between F and S is 90, right? Let's say your F is like this and your S is like that, okay? So in this case, what is your angle between F and S? 90. So since this is 90, you see 0, right? Cosine 90 is 0, you get 0 work done, okay? 0 joule, right? So in the same way, if your angle is like 180 degree, okay, meaning your displacement is this way and your force is this way, the angle is 180 degree, then in that case cosine 180 is -1 and you get minus Fs. Okay, okay, let's do an example here. So pulling a suitcase on wheels. So find the work done if the force is 45 Newton and the angle is 50 degrees and the displacement is 75 meters. So what is the work done? Work done is F cosine theta times S. What is theta? Theta is the angle between F and S. Okay, so it's very easy. This theta is the angle between S and F. Okay, so keep that in mind. In our case, what is the angle between F and S? So this angle, this is F, this is S, the angle is 50 degrees and the force is 45 Newton and your displacement is 75 meter. Okay, this is 75 meter. All right, so let's plug in the numbers here. So F equals 45 cosine 50 degrees times S, which is 75. So if you multiply them together, you happen to get 2170 joule. All right, this is how you figure out your work done. All right, so let's do another example here. So you can see here a person is raising the barbell and he lowers it too. So he raises and lowers the barbell at a constant velocity. Therefore, it is in equilibrium. When there is a constant velocity, the system is in equilibrium, right? That's what we said in the previous lectures. So equilibrium means summation F equals 0. Summation F equals 0 means velocity is constant. Okay, either the object is at rest or the object is moving with constant velocity. Okay, so the barbell is raised and lowered at a constant velocity, therefore is in equilibrium. Since the gravity is acting down all the time, so you have to apply the force upward all the time because gravity always pulls it down. If you do not apply force up, then you cannot hold the object, right? So since gravity is always downward, you should apply the force always upward. Okay, all right, so when you raise it, So you have to apply the force upward. When you lower it, still you have to apply the force upward, okay? Because gravity is always down, all right? So if barbell weighs 500 Newton and the person raises to 0.5 meter above the chest, now what is the work done? In raising, now you need to find the work done in raising and lowering. So remember, gravity is always down. That's why applied force is always up. So applied force is up, applied force is up in both cases, okay? But when you raise, your displacement is up, means force and displacement in the same direction. That's why your cosine of 0, right? So that's why your angle is 0 and cosine of 0 is 1. So it means you get F times S, which is Fs. So you simply multiply 500 times 0.5 and you got 250 joule. Okay. Similarly, when the guy lowers the barbell, what happens is his displacement is downward, right? But he should apply the force upward. See, this is his applied force. So, but the displacement is downward. So, what is the angle between F and S? 180, right? So that's why cosine 180 is -1, and F times S times -1 is negative Fs. So now if we plug in the values, you get 500 times 0.5, but with minus sign, okay? That gives you -250 joule, okay? First of all, let's find the work done by a supermarket checkout attendant on a can of soup when he pushes 0.6 meter horizontally with a force of this. So your force is 5 Newton. What is the displacement? Displacement is 0.6 meter. So are these two, what is the angle between these two? He pushes 0.6 meter horizontally, right? So that's why the force is this way and displacement is this way. Okay, they are in same direction, the angle is 0. Okay, the angle between parallel lines is 0, right? So that's why F cosine 0 S, that's my work done, which is F. Let's see, let's plug in the value of F. F is 5 and cosine 0 is 1 and S is 0.6. If you do that, you end up getting 3 joule. So let's see other tail question here. Express your answer in joules and kilocalories. So, okay, we have to do this in joule and kilocalorie. So we did that in joule. Now let's do that in kilocalorie. So what is the conversion between joule and kilocalorie? So 4.186 joule is equals 1 calorie. Okay. Then how about the kilocalorie? Kilocalorie means multiply both sides by 1000, right? That's how you get kilocalorie. This is 1 kilocalorie and this is 4186 joule. So this is the conversion factor. Based on this, can you convert your 3 joule to kilocalorie? Let's do that. So 3 joule multiplied by 1, right? So 3 joule, so what is 1 here? You want to convert your joule to kilocalorie, right? So you want to cancel the joule. That's why you want to have joule on the bottom and this on the top. So 1 kilocalorie on the top and 4186 on the bottom. So this joule and joule cancel out. If you do that, you end up getting, let me write this here. Let me write this here, okay? You end up getting 7.1710 to the -4 kilocalorie. That's the answer, okay? Now, B, the gravity. Now the work done by gravity on a can of soup. So gravity is like this, mg, right? Now the displacement is this way. So what is the angle between the force and the displacement? 90. So that's why work done equals F cosine 90 times S. So since cosine 90 is 0, your work done is 0. Okay. So in this slide, we'll be talking about work energy theorem and kinetic energy. So now we are slowly moving towards energy from the work. Okay. So mainly in this course, we'll be talking about mechanical energy, and there are two kinds of mechanical energy. One, the kinetic energy, and the other one is potential energy. Okay. So we'll be talking mainly two kinds of energy, two kinds of mechanical energy. All right. So let us consider a constant net external force acting on an object. So like this, right? Constant force is acting on the object like this in the direction of the displacement. Okay. So here the net force is summation F and the displacement is S. So since they are in the same direction, so what is your work done? Work done is F summation F times cosine theta. Yes, so since F and S are in the same direction, theta is 0, so cosine 0 is 1. So you end up getting W equals summation Fs, right? According to Newton's second law, what is your summation F? Summation F is ma, right? That's why you have mas. All right. So work is mas, right? So that's what we did in the previous slide. Now, remember our 3 lines of the Bible? So one of them is this. Okay. Now in our case, our displacement is now S, okay, not X. Displacement is X. The displacement is S. So okay, this is my displacement. So this AS. So from here, how do you find AX? So AX is, let's do it here. So B, subtract B0 square on both sides. Then you can cancel out. Then what do you get here? BF square minus B0 square equals to AX, right? So divide both sides by 2, what do you get? You have AX, which is this, right? AX equals 1 over 2 BF square minus B0 square, okay? Which AX is something as AS, right? So that's why this guy replaces this guy, okay? M times 1/2 BF square minus B0 square. That's the thing here, okay? Now you just distribute your 1 over 2m. 1 over 2m BF square, that's what it is. 1 over 2m B0 square, that's what it is. So you have negative sign in between, okay? All right, so now let's, what is kinetic energy? Kinetic energy of an object with mass m and speed v is given by this formula, as you might be familiar to it. So kinetic energy is given by 1 over 2 mv squared, where m is the mass of the object which is moving, and v is the speed of the object in motion. Okay, this is the definition of kinetic energy. Now, so can I say this is the final kinetic energy? So mass does not change. Bf, final velocity, that's why KEF. This is final kinetic energy. Mass does not change. V0, initial velocity, that's why this is initial kinetic energy. Okay, so that's why work and kinetic energy are related like this, which is like this. Okay, so work is related to change in kinetic energy. Okay, that's called work energy theorem. All right. So a driver in a 1,000 kilogram car traveling at 24 meters per second slams on the brakes and skids to a stop. If the coefficient of kinetic friction between the tires and road is 0.8, how long are the skid marks? So suppose the driver in a 1,000 kilogram car is traveling at this 24, right? B0 is 24 meter per second. He slams on the brake, meaning there is a friction. Brake means friction, right? Without friction, there is no brake. You cannot apply, even though braking means applying friction, okay? Let's put it that way. So when he applies a brake, okay, meaning he's going to stop it. So there is skid until I stop. So it skids to a stop. Okay. So this is everything here is stop, skid mark. So this is the stop. This is where your car stops. Now, if the coefficient of the kinetic friction between the tires and the road, okay, so mu k is 0.8, right? How long are the skid marks? So what is the distance traveled by the car before it stops? Okay, that's the length of the skid mark, right? First of all, let's figure out your friction force. So friction is fun, right? F equals mu k Fn, right? Mu k n, right? Okay. So what is the normal force of the car? So assuming the road is labeled L-E-V-E-L-E-D, labeled, so we can say N equals mg, right? So normal force equal to the weight of the car. So mu k times mg, right? Okay. All right. So now in this case, force. What is the force that acts on the? What is the force that act on the car? The friction force. Okay. So friction force does the work. So meaning work done equals F cosine theta and D. D is the length of the skid mark. So in this case, what is theta? The force, friction force is this way. Okay. Friction force applies to the opposite to the motion. So F and D, they are in opposite direction. That's why your cosine is 180. So you end up getting work done is negative. Your work done is negative. F is mu k, right? Mu k mg, right? Negative mu k mg cosine 180 is -1. This is how you get the negative sign. Then D there. So what is your mu? Mu is 0.8 right here. Then what is your m? M is 1000. What is your G? 9.8, obviously. Then what is your D? D is D. We don't know the D yet, right? Let's use the work done and kinetic energy theorem. So work done equals KEF minus KE initial. So finally, it will be at the rest, right? So that's why KEF is 1/2 m VF square, which is 0, because it will be at rest, minus 1/2 m VI square. So we know the initial velocity, 24. So equals minus 1/2 m is 1000. VI is 24 square. So what is your work done then? Work done is this. And this is your change in kinetic energy. According to the work energy theorem, so this should be equal, right? Meaning this guy must be equal to this guy. Okay, let's do that. So meaning minus 0.8 1000 9.8 D must be equal to minus 1/2 1000 24 square. You need to find D, right? So divide both sides by minus 0.8 1000 9.8. Okay, minus 0.8 1000 9.8. So 1000 cancel out, minus cancel out, and if you do this calculation, you end up getting, okay, I'll give you the answer here, you end up getting 36.7 meter. Okay. All right, so let's do another work energy theorem, and let's do another example on work energy theorem and kinetic energy. The mass of the space probe is 474 kilogram and its initial velocity is 275 meter per second. If the 56 millinewton force, okay, act on the probe through a displacement of 2.4 to 10 to the 9 meter, what is its final speed? Okay, that's the thing we need to figure out. Let's do it. Okay, so what is millinewton? Millinewton is, what is the your force is, let's write this down here. So your force, the mass is 474 kg. Okay, and initial speed is v0 is 275 meter per second. So force is 56 millinewton. Okay, so it means 56 divided by 1000, which is -3 Newton. Okay, all right. Now, yeah, displacement S is 2.42 10 to the 9 meter. Okay, now we need to find the final V. So we know the formula, work done equals delta Ke, which is 1/2 mvf square minus 1/2 mv0 square. Okay, so that's the formula we have. Now let's plug in the value of W. W is, what is W? W is F cosine theta S equals 1/2 mvf squared minus 1/2 mv sub 0 squared. Okay. So if you take a look at this picture here, the force and displacement are in the same direction, right? So that's why your cosine theta is cosine 0, right? So F cosine 0 S. So which means F times S, right? So what is the force? Let's plug in the values now. The force is this 56 10 to the -3. Then S is 2.42 10 to the 9 equals 1/2. You can factor out M. So M is 474 VF. VF is how much? We don't know. This is VF, right? VF is VF minus V0 is 275 squared. Okay. So now if you multiply both sides by 2, then you cancel this 2. Divide both sides by 474. 474. You got that. It's cancelled out. Then add both sides by, add both sides 275 squared. 275 squared. And this cancel out. Then your VF square is, VF is the square root of, right, 2 times 56 10 to the -3, 2.42 10 to the -10 to the 9 divided by 474 plus 275 squared. Okay, if you do that, if you do this calculation, you end up getting 805 meter per second. All right. So in this slide, we'll be talking about gravitational potential energy. Okay, suppose you have a ball here at a height of h0, and this ball has the potential energy of mgh0. This ball has the potential energy of mgh0, right? So mgh0. So meaning, if something is at a height of h0, then potential energy is the product of its weight with the height. Okay, so mg is the weight and h0 is the height. That's the definition of a gravitational potential energy. So what is the unit of potential energy? Again, this is joule, right? Unit is again joule, because energy is energy and it has the unit of joule. In this case, I'm going to talk about the work done by the gravitational potential energy. Okay, so as you know, work done is given by this. And in the case of in this example, so what is the displacement? Suppose you let it, if let the ball fall through the displacement s, then your force is mg, right? Force is mg, and the mg is acting down and s is acting down. So mg is acting down and s is in the downward direction. That's why the angle between them is cosine. Angle between them is 0 and cosine 0. So s is s, right? So mg s. But this s can be written as h0 minus hf. So let's do an example here. A gymnast on a trampoline. The gymnast leaves the trampoline at an initial height of 1.2 meter and reaches the maximum height of 4.8 meter before falling back down. What was the initial speed of gymnast? Okay. So we are given that initial height is 1.2 meter and the final height is 4.8 meter. Okay. So when it reaches the maximum height, the velocity is 0. Okay. Final velocity is 0. So we need to have some initial velocity, otherwise it cannot go up. So you need to find that initial velocity. So let's do the work energy theorem here. So which is W equals 1 over 2 mBF square minus 1 over 2 mBg square. Let's figure out the work done by the gymnast. Equals 1 over 2, we don't know the mass. But you can factor out mass, by the way, Bf square minus Bg square. So what is your final velocity? Final velocity is 0 square minus initial velocity is Bg square. Okay. This is the work done by the gymnast. Let's find the work done by the gravity here. Work done by gravity is F cosine theta S, right? So your F is gravity, which is mg. So your S is here up and gravity is acting down. That's why this is cosine 180. Then what is the S? S is going from here to here, means S is positive, right? So how much is the S? S is 4. So HF is 4.8 meter and H0 is 1.2 meter. So 4.8 minus 1.2 meter. So both of them are work done, right? So they should be equal. That's why 1 over 2 m, 1 over 2 m b0 square minus b0 square equals mg. This is minus, right? You can add minus here. Then 4.8 minus 1.2. Okay. So divide both sides by m. Right. Divide both sides by g. You get that. This and this cancel out. This minus and this minus cancel out. You got, so 1 over 2 b0 square over g equals 3.6, right? Multiply both sides by g times 2, right? 2 times g. So g and g cancel out, 2 and 2 cancel out. So b0 square equals 3.6 g times 2. So b0 equals square root of that. So which is, if you plug in the value of 3.6, 9.8 times 2, we end up getting 8.4 meter per second. Okay. Now in this slide, we'll be talking about the conservation of mechanical energy. So as I said earlier, what is mechanical energy? Mechanical energy is mechanical energy ME equals KE plus PE. Okay. So what does the conservation of mechanical energy tell you? So energy can neither be created nor be destroyed. All right. So Another approach is to say that, in other words, total mechanical energy of an isolated system remains constant. Okay. In other words, KE1 plus PE1 equals KE2 plus PE2. Okay. All right, let's do an example here. A motorcyclist is trying to leap across the canyon by driving horizontally off a cliff 38 meters per second. Ignoring air resistance, find the speed with which the cycle strikes the ground on the other side. So this guy takes a huge jump from here to here. So he goes from the height of 70 meter to the height of 35 meter, right? So how do you do this problem? So you know the initial velocity, initial height, and final height. You need to find the final velocity, okay? Let's use the principle of conservation of energy and let's figure this out. So principle of conservation of energy says final EF equals initial EF. So what is your final EF? Again, this is the sum of two energies, right? So mgHF plus 1 over 2 mBF equals mghi plus 1 over 2 mbbi plus 1 over 2 mbi squared. Okay, that's your conservation of energy. Now m is we have m everywhere, so you can divide this by m, this by m, this by m, this by m, then your m cancel out. Then you have GHF plus 1 over 2 BF squared equals GHI plus 1 over 2 MBI squared. So from the previous slide, you have, let me rewrite this, plus 1 over 2 BF squared equals GH0 plus 1 over 2 B0 squared. Okay. So what is your BF? So subtract minus GHF from both sides. What do you get? So this cancel out. Then you're left with 1 over 2 BF squared equals G. You can factor out G from here. Then H0 minus HF plus 1 over 2 B0 squared. If you multiply both sides by 2, you have 2 here, you have 2 here. These two to cancel out, this cancel out, then your BF equals square root of 2G H0 minus HF plus 1 plus B0 squared, right? So let's plug in. 2G is 9.8, obviously. What is your H0? H0 is 70, right? 70, oops. 70 minus HF is 35 plus B0 squared is 38 squared. So if you do the calculation, you end up getting 46.2 meter per second. Okay. All right. So let's do the definition of power. Then we are done with this chapter. Okay. So definition of average power. So what is power? Power is rate of doing work, right? Okay. So if you know the work and time in which the work is done, so time taken to accomplish that work, then your average power is total work done by total time. So which is work over time, meaning W over T. So what is the unit of power? Unit of power is work has the unit joule and time has the unit second. So joule over second or joule per second, and also we call it watt. Okay, after the name of the scientist, James Watt, and we can simply call it W. Okay, that's the unit of power. So power also can be defined in terms of energy. So we know average power is work over time. Similarly, average power also can be defined in terms of change in energy over time. Okay. Okay, the other unit of power is horsepower, which is frequently used in industry, and horsepower is equal to 740. 1 horsepower equals to 745.7 watts. Okay, there is another formula for power, which is force times speed. Okay, power equals force times speed. With this, I want to conclude this chapter. Thank you.